Regular computers handle information by breaking it down into bits. Each bit can be described as a 1 or a 0, but quantum computers are made of quantum bits, or qubits. Thanks to something called quantum superposition, a qubit can exist as both a 1 and a 0 at the same time. Superposition is a quality of quantum mechanics that means that a particle or a photon can exist in all of its possible states at the same time, and will only settle on a state when it is forced to decide by being observed. You can think of it as being like a coin toss. When a coin is spinning through the air, it could be said to exist as both the heads and tails at the same time. It's only when the coin is observed by landing on a tabletop that it decides which state to occupy. Quantum computers are made up of multiple entangled qubits, with all of their superpositional states connected together. Entanglement is another oddity of quantum mechanics. At its most simple, it means that two or more particles are connected through a sort of quantum Wi-Fi network. This connection means that each of the qubits reacts to a change in another qubit's state instantaneously, no matter how far apart they are. So just by measuring the properties of one entangled qubit, you can instantly know the properties of its partners without having to look at them. Because each qubit exists in multiple states, it can make multiple calculations simultaneously. Add more entangled qubits, and the number of possible calculations the quantum computer can make increases exponentially. What it means is, rather than having to run a calculation many times, you can, in theory, run every conceivable calculation at once. Imagine you're a delivery company and you want to pick the best route from A to B, but you also have to make 150 deliveries on the way. To find the most efficient route, a normal computer will have to look at tens of thousands of options individually and then compare the results. Because the quantum computer exists in many states at once, it can look at many different routes at once and determine the best ones almost instantaneously. Complex calculations like these with loads of different variables can become thousands of times faster. Unfortunately, just adding more qubits is not as easy as it sounds. Adding more bits to a normal computer is simple, but in quantum computers, the more qubits you have, the more unstable the system becomes. This makes it incredibly difficult to add more qubits and scale up a quantum computer processor. What's more, superposition and entanglement are very unstable states, and the slightest interference, such as vibrations or radiation, can cause these states to be disturbed or collapse. This is called quantum decoherence, and when this happens, the broken qubit must be replaced. This means that qubit-based processors need to be kept carefully isolated from the outside world by using vacuums, dampening vibrations, and shielding them from radiation. Due to this level of complexity, you're unlikely to ever have a quantum computer on your desk or in your pocket.